welcome to this problem walkthrough. In this video, we'll explore problem number 907, sum of subarray minimums. This is a fascinating problem that challenges us to calculate the sum of the minimum values of all possible subarrays of an input array. We'll dive into different approaches, analyze their complexities, and discuss when each solution is appropriate. Let's get started. In this problem, you are given an array of integers, where each element in the array represents a specific value. Your task is to calculate the sum of the minimum values of all possible subarrays of this array. Because the result could be extremely large, you are required to return the sum modulo 10 to the power of 9 plus 7, which ensures the output remains manageable. For the input format, the array can have a length between 1 and 30,000, and each element in the array is guaranteed to be between 1 and 100,000. The output of this problem is a single integer, representing the sum of these minimum values, modulo 10 to the power of 9 plus 7. To better understand the problem, let's start by looking at an example. Suppose the input array is 3, 1, 2, 4. The goal is to calculate the sum of the minimum values for every subarray of this array. Let's break this down. The first subarray is 3, and its minimum value is 3. For the next subarray, 3, 1, the minimum is 1. Expanding further to 3, 1, 2, the smallest value remains 1, and for the entire array, 3, 1, 2, 4, the minimum is still 1. Continuing, we evaluate subarrays starting at the second element, 1, 1, 2, and 1, 2, 4, all of which have a minimum of 1. Subarrays starting at the third element include 2 and 2, 4, with minimums of 2 for both, and finally, the last subarray, 4, has a minimum of 4. When we add all these minimums together, we'll compute the total sum. The sum of all the minimum values from the subarrays of 3, 1, 2, 4 is 3 from 3, 1 from 3, 1, another one from 3, 1, 2, and yet another one from 3, 1, 2, 4. From the subarray starting at the second element, we add 1 from 1, another one from 1, 2, and yet another one from 1, 2, 4. Then, we add 2 from 2, another 2 from 2, 4, and finally 4 from 4. Adding these values gives us 3 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 2 plus 2 plus 4, which equals 17. Looking at another example, if the array is 11, 81, 94, 43, 3, the process is similar. We calculate the minimums for all subarrays, sum them together, and take the result modulo 10 to the power of 9 plus 7. After performing these computations, the final result comes out to 444. To solve this problem efficiently, we need to consider how different types of arrays affect the calculation. For instance, in a single element array like 1, the result is simply the value of that single element. When all elements in the array are equal, such as 2, 2, 2, each element contributes to subarrays of different sizes, and the sum can be calculated systematically. Arrays with strictly increasing values, like 1, 2, 3, or decreasing values, like 3, 2, 1, create predictable patterns in how the minimums propagate through the subarrays. Finally, for very large arrays, such as one with 30,000 elements where each value is the maximum of 100,000, it becomes crucial to use an optimized approach to handle the calculations efficiently within the constraints. To start, let's explore the brute force approach. The idea here is straightforward: calculate the minimum value for every possible subarray of the input array. For each subarray, we determine its minimum and add that value to our cumulative sum. While this approach is intuitive, it involves iterating through all subarrays, which takes n squared time, and then finding the minimum for each subarray, which requires n for each iteration. This results in an overall time complexity of n cubed. The main drawback of this method is that subarrays overlap, meaning we end up recalculating the same minimum values multiple times, leading to significant inefficiencies. For larger arrays, this approach quickly becomes computationally prohibitive. To address these inefficiencies, we turn to a more optimized solution using a monotonic stack. The key insight here is to calculate each element's contribution as the minimum of certain subarrays without explicitly iterating through all subarrays. This avoids redundant computations and forms the basis of our optimized approach. Now, let's break down the core observations that power the optimized approach. Each element in the array contributes as the minimum for a specific range of subarrays. This range is determined by the nearest smaller elements on both sides. Specifically, for any element ARR, I, we define previous, I, as the index of the nearest smaller element to the left, and next, I, as the index of the nearest smaller element to the right. Using these indices, the total number of subarrays where RR, I, is the minimum can be calculated as I previous, I, asterisk, next, I. Multiplying this count by ARR, I, gives the total contribution of the element to the overall sum. To find previous, I, and next, I, efficiently, we use monotonic stacks. These stacks allow us to calculate both indices in O, N, time. The algorithm proceeds in 3 steps. First, compute previous, I, using a monotonic increasing stack while iterating from left to right. Then, compute next, I, using another stack while iterating in reverse. Finally, calculate the contribution of each element using the formula and sum the results, taking care to apply modulo 10 to the power of 9 plus 7 is required. This approach brings the time complexity down to O, N, while using O, N, space for the stacks. The monotonic stack approach stands out as the chosen strategy due to its efficiency and elegance. Unlike brute force, which repetitively recalculates the same minimums, this method leverages the properties of monotonic stacks to greatly reduce unnecessary computations. By determining the previous and next indices in linear time, we achieve an overall complexity of O, N, which is a significant improvement. When comparing the two approaches, the brute force method has the advantage of being simple to understand and implement. However, its O, N cubed complexity makes it impractical for large inputs. On the other hand, the monotonic stack approach is highly efficient and scalable, with an O, N runtime that can handle much larger arrays. While it is slightly more complex to implement, the trade-off is well worth it given the performance gains. For this problem, the constraints make the monotonic stack approach the clear choice, offering both speed and scalability to handle large datasets effectively. To understand the problem, we are given an array ARR, and our task is to compute the sum of the minimum values of all possible subarrays. A subarray is simply a contiguous portion of an array. The brute force approach to solve this begins by initializing a variable called total_sum to 0, which will store the cumulative result. The size of the array, n, is used to control the range of our iterations. The solution then involves generating all possible subarrays using 2 nested loops. The outer loop sets the starting index I of the subarray, while the inner loop determines the ending index j. For every subarray that these indices define, we need to identify its minimum value. This can be done by iterating through all the elements of the subarray and finding the smallest one. This value is then stored in a temporary variable, such as current_min, for further processing. After calculating the minimum value of a subarray, current_min is added to total_sum. This process is repeated for all subarrays, ensuring that every possible configuration is considered. Finally, after the nested loops complete, total_sum holds the desired result, which is returned as the output. Analyzing the time complexity, generating all subarrays requires 2 nested loops, resulting in O, N squared, complexity. Within each subarray, finding the minimum value through iteration takes O, N, in the worst case. When combined, the overall time complexity of this brute force approach is O, N cubed. While this guarantees correctness through exhaustive computation, it is highly inefficient for larger arrays. The brute force approach works because it explicitly calculates the minimum value of every subarray, ensuring correctness. However, its inefficiency arises from repeatedly recalculating the minimum for overlapping subarrays. For example, when processing subarrays that start at the same index I, the minimum values for subarrays ending at j and j plus 1 significantly overlap. This redundancy causes unnecessary work. In terms of edge cases, the approach handles single-element arrays correctly, as the minimum is the element itself. For uniform arrays, such as 1, 1, 1, all subarrays have the same minimum, leading to repetitive additions of the same value. For arrays that are strictly increasing or decreasing, the method still works correctly but highlights inefficiencies due to repeated calculations. The brute force solution primarily relies on the array ARR and index-based subarray generation. The variable total underscore sum accumulates the final result, while current underscore min temporarily stores the minimum value of the current subarray. To overcome the inefficiency of recalculating overlapping minimums, we can use a more optimized approach based on a data structure called the monotonic stack. This method allows us to calculate each element's contribution as the minimum of subarrays in O(n) time. The key idea is to determine how many subarrays have the current element as their minimum. To achieve this, we use the monotonic stack to find the nearest smaller elements on both the left and right sides of each element. By doing so, we can directly compute the number of subarrays for which the element serves as the minimum without explicitly generating all subarrays. The optimized approach involves several key operations. For each element in the array, we calculate the number of subarrays where it is the minimum. This is done by multiplying the distances to the nearest smaller elements on the left and right sides. The element's value is then multiplied by this count and added to the cumulative sum. The time complexity of this approach is O(n), as each element is pushed and popped from the stack exactly once. To implement this, we begin by initializing two arrays, left and right, which will store the distances to the nearest smaller elements on the left and right respectively. A monotonic stack is used to efficiently calculate these distances. First, we iterate through the array to calculate the left distances. For each element, the stack helps us find the nearest smaller element on the left, and the distance is stored in the left array. Next, we calculate the right distances by iterating through the array in reverse. Using the monotonic stack, we find the nearest smaller element on the right for each element and store the distance in the right array. Once we have both the left and right distances, we calculate each element's contribution to the total sum. For an element I, the number of subarrays where it is the minimum is given by left, I, asterisk right, I. We multiply this value by the element itself and add the result to the cumulative sum. After processing all elements, the cumulative sum contains the desired result, which is returned as the output. This optimized approach avoids the inefficiencies of the brute force method, achieving the same result with significantly improved performance. Here, we begin the Python implementation of the sum of subarray minimums problem. The function sumSubarrayMin starts by defining a constant mod, which will be used to take results modulo 10 to the power of 9 plus 7, as required by the problem statement. We also determine the length of the input array, arr, and initialize two arrays, prev_smaller and next_smaller. These arrays will help us track the indices of the previous and next smaller elements for each element in the array. Initially, prev_smaller is filled with -1, implying no smaller element to the left, and next_smaller is filled with n, indicating no smaller element to the right. Next, we use a monotonic stack to populate the prev_smaller array. The stack helps us efficiently find the last smaller element to the left of the current index. As we iterate through the array, we pop elements from the stack while the top of the stack represents a value larger than the current element. After updating prev_smaller, we push the current index onto the stack. Similarly, we use another monotonic stack to compute the next_smaller array, this time iterating from the end of the array toward the beginning. This ensures we find the first smaller element to the right of each index. The logic is similar, we pop elements from the stack while the value at the top of the stack is greater than or equal to the current element. Once this is done, the arrays prev_smaller and next_smaller contain the distances to the nearest smaller elements on both sides for all indices. Now that we have the prev_smaller and next_smaller arrays, we can calculate the sum of subarray minimums. For each index I in the array, we compute left_count, which is the number of subarrays where the current element is the smallest and extends to the left. This is given by the difference between the current index and the previous smaller index. Similarly, right_count is the number of subarrays extending to the right, where the current element is the smallest, and is calculated as the difference between the next smaller index and the current index. The contribution of the current element to the final result is then the product of the element's value, left_count, and right_count. This ensures we capture its role as the minimum in all its valid subarrays. We add this contribution to the result and take modulo mod to handle large numbers. Finally, after iterating through all elements, we return the computed result. Here, we're implementing the solution for the sum of subarray minimums problem in Java. We start by defining the method SumSubarrayments that takes an array of integers as input. To handle large results, we use a modulo value mod set to 10 to the power of 9 plus 7. Next, we initialize the array size n and create two auxiliary arrays, prev smaller and next smaller. These will store the indices of the previous and next smaller elements for each element in the input array. Initially, prev smaller is filled with -1, indicating no smaller element to the left, while next smaller is filled with n, indicating no smaller element to the right. To find the previous smaller elements, we use a monotonic stack. We iterate through the array, and for each element, we ensure that the stack only contains indices of elements smaller than the current one. If the stack's top element is greater, we pop it. Once the stack is in a valid state, the top of the stack gives us the index of the previous smaller element. If the stack is empty, it means no smaller element exists, so we leave the value as -1. The current index is then pushed onto the stack for future comparisons. This prepares us for efficiently determining the previous smaller elements for all indices. Now, we use a similar approach to determine the next smaller elements, but this time, we iterate from the end of the array towards the beginning. For each element, we maintain the stack to ensure it only contains indices of elements smaller than or equal to the current one. If the top of the stack represents a larger or equal element, we pop it. Once the stack is valid, its top gives us the index of the next smaller element. If the stack is empty, it means no smaller element exists, so we leave the value as n. The current index is then pushed onto the stack. With both prev smaller and next smaller arrays prepared, we now calculate the sum of subarray minimums. For each element in the array, we compute two counts, left count, representing the number of subarrays ending at the current index, and right count, representing the number of subarrays starting at the current index. These are derived using the distances to the previous and next smaller elements. The contribution of each element to the result is its value multiplied by these counts, and we accumulate this contribution into result, taking modulo mod to handle large values. Finally, we return the result as an integer. To solve this problem, we start with the given input array arr equals 3, 1, 2, 4. We'll also define a large modulo constant mod equals 10 to the power of 9 plus 7 to handle potential overflow, and determine that the array length n equals 4. Two helper arrays prev_smaller and next_smaller are initialized, both with default values. Prev_smaller is filled with -1 to indicate no smaller elements to the left initially, and next_smaller is filled with 4, the length of the array, for no smaller elements to the right. Next, we calculate the prev_smaller array to find the closest smaller element to the left for each index. Using a monotonic stack, we iterate through the array. For I equals 0, the stack is empty, so prev_smaller, 0, remains -1. We push 0 to the stack. At I equals 1, since arr, stack, -1, arr, 1, we pop 0 from the stack, set prev_smaller, 1, to -1, and push 1. For I equals 2, arr, stack, -1, arr, 2, so we set prev_smaller, 2, to 1 and push 2. Finally, at I equals 3, arr, stack, -1, arr, 3, so prev_smaller, 3, is set to 2, and 3 is pushed to the stack. The result of this step is prev_smaller equals, -1, -1, 1, 2. Now, we move on to finding the next _smaller elements. For this, we reset the stack and iterate through the array in reverse. At I equals 3, the stack is empty, so next_smaller, 3, remains 4, and we push 3. At I equals 2, since arr, stack, -1, equals arr, 2, we pop 3, set next_smaller, 2, to 3, and push 2. For I equals 1, arr, stack, -1, equals arr, 1, so we pop 2, set next_smaller, 1, to 4, and push 1. Finally, at I equals 0, arr, stack, -1, equals arr, 0, does not hold, so we leave next_smaller, 0, as is and push 0. The result is next_smaller equals 1, 4, 3, 4. With both prev_smaller and next_smaller computed, we can calculate the contribution of each element to the sum. For each index I, we determine left underscore count as the number of subarrays ending at I where I is the minimum, and right underscore count as the number of subarrays starting at I with I as the minimum. For I equals 0, left underscore count equals 1, right underscore count equals 1, so the contribution is 3*1*1 equals 3. For I equals 1, left underscore count equals 2, right underscore count equals 3, giving a contribution of 1*2*3 equals 6. For I equals 2, left underscore count equals 1, right underscore count equals 1, so the contribution is 2*1*1 equals 2. Finally, for I equals 3, left underscore count equals 1, right underscore count equals 1, resulting in a contribution of 4*1*1 equals 4. Summing these contributions gives a total of 3 plus 6 plus 2 plus 4, % mod equals 15. The final result for this example is 15. Now, let's consider another example with a different input array, r equals 11, 81, 94, 43, 3. As before, we initialize mod equals 10 to the power of 9 plus 7, n equals 5, and set up preb underscore smaller with all -1 values and next underscore smaller with all 5. First, we calculate preb underscore smaller using the stack. After iterating through the array, the result is preb underscore smaller equals -1, 0, 1, 0, -1. Then, we find next underscore smaller by iterating in reverse, which results in next underscore smaller equals 4, 3, 3, 4, 5. Finally, we calculate the total contribution for each element in the array. For r 0 equals 11, the contribution is 11*1*4 equals 44. For r 1 equals 81, the contribution is 81*1*2 equals 162. For r 2 equals 94, the contribution is 94*1*1 equals 94. For r 3 equals 43, the contribution is 43*3*1 equals 129. For r 4 equals 3, the contribution is 3*5*1 equals 15. Adding these together gives a total of 44 plus 162 plus 94 plus 129 plus 15 equals 444. Thus, the final result for this example is 444. The time complexity of this solution is O(n), and we can break it down into 4 distinct steps. First, initializing the arrays preb underscore smaller and next underscore smaller takes O(n) time since we allocate space for these arrays based on the input size. Next, we find the previous smaller elements for each index. This involves iterating over the array once, and thanks to the amortized efficiency of stack operations, where each element is pushed and popped at most once, this step takes O(n). Similarly, finding the next smaller elements follows the same process, iterating through the array once and using stack operations efficiently, resulting in another O(n) time complexity. Finally, we calculate the sum of subarray minimums by iterating over all elements and performing constant time arithmetic for each, which also takes O(n). Altogether, each of these steps contributes linearly to the overall time complexity. When we combine these steps, we add O(n) for initialization, O(n) for finding previous smaller elements, O(n) for finding next smaller elements, and O(n) for calculating the sum of subarray minimums. This results in a total time complexity of O(n) plus O(n) plus O(n) plus O(n), which simplifies to O(n). Now, examining the space complexity, the auxiliary arrays preb underscore smaller and next underscore smaller each require O(n) space since they are of size n. The stack used for monotonic computations also requires O(n) space in the worst case, such as when the input array is strictly increasing or decreasing, as all elements might be added to the stack. Other variables like mod, n, result, and loop counters contribute O(1) space. Combining these, the total space complexity is O(n) for the arrays, O(n) for the stack, and O(1) for the constants, which simplifies to O(n). To understand the efficiency of this approach, let's compare it to a naive or brute force solution. In the naive approach, we would generate all possible subarrays, which takes O(n squared, for an array of size n. Then, for each subarray, finding the minimum element would take O(n) in the worst case. Multiplying these together gives an overall time complexity of O(n squared, O(n), or O(n cubed). In contrast, the optimized approach leverages monotonic stacks to determine the contribution of each element efficiently. By avoiding redundant computations and directly calculating contributions, the optimized algorithm reduces the time complexity to O(n), while ensuring correctness. This is a significant improvement over the brute force O(n)³ solution. The time complexity of O(n) can be mathematically verified by analyzing the stack operations and loops. In the monotonic stack operations, each element is pushed once and popped at most once, resulting in a total of 2n stack operations, which is linear. Additionally, each loop in the algorithm traverses the array once, with no nested loops or repeated operations, ensuring the time complexity remains O(n). For space complexity, the auxiliary arrays in the stack dominate the usage, both requiring O(n) in the worst case. Looking at best, average, and worst case scenarios, the runtime remains O(n) in all cases. For example, in the best case where all elements are equal, each element is processed exactly once. In the average case for a random array, the amortized efficiency of stack operations ensures linear runtime. Even in the worst case, such as a strictly increasing or decreasing array, each element is pushed and popped once, maintaining O(n) efficiency. In summary, the optimized solution achieves a time complexity of O(n) and a space complexity of O(n), making it significantly faster and more space efficient than the naive O(n)³ approach, thanks to the use of monotonic stacks. When solving this problem, there are several common mistakes to watch out for. First, not optimizing for large inputs is a critical error. If you use a brute force approach, which often has a time complexity of O(n²), or worse, you'll run into performance issues for constraints where n can go up to 10 to the power of 4. This will almost certainly lead to a time limit exceeded error. Efficient solutions are necessary here. Another frequent issue is ignoring edge cases. For example, if you don't handle scenarios like empty arrays, single-element arrays, or arrays with repeated elements, your solution could produce runtime errors or incorrect results. Subarray boundary errors are another pitfall. It's common to see off-by-one mistakes in indices, which can result in excluding valid subarrays or including invalid ones, leading to incorrect answers. Lastly, overcomplicating the logic is a trap many fall into. Using unnecessary data structures or excessive calculations not only increases the risk of bugs but also makes your code harder to debug and maintain. Simplicity is key for both correctness and readability. Another common mistake is not leveraging known patterns that simplify the problem. For instance, using a monotonic stack or prefix arrays can reduce time complexity significantly and often lead to more elegant solutions. Missing these patterns can make your code unnecessarily complex and inefficient. Now, let's discuss some key insights for interviews. First, always analyze the problem constraints before you start coding. Understanding the input size will help you determine the most efficient approach to take. It's also important to explain your thought process clearly. If you begin with a brute force solution, make sure to articulate how you plan to optimize it. This demonstrates clarity and problem-solving skills, which interviewers value. Additionally, it's crucial to know common patterns, such as sliding windows, prefix sums, or monotonic stacks, especially for subarray or substring problems. These techniques are frequently tested in interviews. Another tip is to optimize incrementally. Start with a straightforward solution, then discuss how to reduce time or space complexity. Lastly, focus on writing clean and readable code. Avoid unnecessary variables or overly verbose implementations, as good readability leaves a strong impression. Once you've mastered the sum of subarray minimums problem, you'll notice that it shares similarities with other important problems. For example, LeetCode 239, sliding window maximum, is another subarray-based problem that teaches you how to optimize using the sliding window technique. Similarly, LeetCode 42, trapping rainwater, is a popular problem that involves monotonic stacks for efficient computation. It's a great way to deepen your understanding of this pattern. Another closely related problem is LeetCode 84, largest rectangle in histogram, which also relies on monotonic stacks to solve range-based queries efficiently. These problems are not only excellent practice for mastering techniques like monotonic stacks, but they also help you recognize recurring patterns in competitive programming and interviews. Developing a strong grasp of these related problems can significantly boost your problem-solving skills. When considering alternative approaches to this problem, it's important to weigh their trade-offs. A brute force solution, for instance, involves generating all subarrays and calculating the minimum for each, which results in a time complexity of O(n cubed). While this is straightforward to implement, it's highly impractical for large inputs due to its inefficiency. A slightly better approach involves using prefix arrays to pre-compute minimums for all ranges. This reduces the complexity to O(n squared, making it faster than brute force, but it's still not optimal for handling larger constraints. The most efficient solution uses monotonic stacks, which bring the complexity down to O(n). This approach is optimal but requires a solid understanding of stack-based algorithms, which can be tricky for beginners. Lastly, dynamic programming can also be applied, with a complexity of O(n squared in most cases. While it's often intuitive and easier to reason about conceptually, it's generally slower than a stack-based approach. Choosing the right method depends on the problem constraints and your comfort with these techniques, but for large inputs, monotonic stacks are usually the best choice. Great job making it to the end. To recap, we tackled the sum of subarray minimums problem and discussed approaches to solve it efficiently. Remember, this problem highlights the importance of balancing clarity and performance in algorithm design. Keep practicing similar problems to reinforce your skills. Thanks for watching, and don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!